In today's video, here is a nice problem that was suggested by viewer for a long time. So by chance I get to this problem. Here is the following information. Let k and m and be integer numbers satisfy these two conditions. The first condition, the GCD of m and n equals 1. So the second condition, we have k square must be a perfect square, which equals the product of m and n. So the question, we are going to prove these integers m and n are perfect square. Okay, let's make the quicker chart. So I'm going to square the integer and divide that integer by 4. You get the remainder 0 or 1. If that integer is even, you get a remainder 0. If that integer is odd, you get a remainder number 1. Okay, it's more simple. So here is the following chart. We get the integer x. We are going to square it. This one it will be reduced to the mod 4. Okay, so get the following values: 0, 1, 2, 3, 4, 5, and so on and so forth. For 0, it's clearly is 0. For 1, is clearly is 1. For number 2, you get 4. 4 is always divisible by number 4, which is 0. 3, it will get 3 square, which is 9. 9 is 1 more than 8. You get a remainder number 1. 4 square, which is 16. You get a remainder 0. 5 is 25. You get a remainder number 1. So you get the set 0, 1, 0, 1, 0, 1. So where is 0? So we get 0 here when we have the value even. So we get the 0 as a reminder when we have this integer even. You get 0, 2, we get 4 here. When we get odd, we get the integer odd, you get the remainder number 1. You see? This is the fact that I'm going to use here to prove this problem. Okay? Now let's get rid of this one and move on to the problem. We are going to break this one into two cases. When we have k is a even and when we have k is a odd. For k is a even, as we just discussed before, we get k is a even, which means k square is always a congruent to 0 mod 4. Okay, by chart. So let's keep this one. Let's keep this one as an original statement. Now let's compare the right hand side of this equation. So if k is a even, so we get k square here, which equals m is multiplied by n. So as we said, if k is a even, which means one of the term is going to be even. Let's assume m is a even, but the other one must be odd. We cannot have both of them is even because of GCD. Because of GCD of m and n equals number 1. Okay, which means m cannot divide n. M cannot divide n. GCD of m and n equals 1 is not just m cannot divide n, but also they are not shared any common divisor. Okay, this is one side. On the other side, if you take a look at the left hand side of this equation, we get k is a perfect square, which means the right hand side of this equation must be a perfect square as well, which means each of these must be a perfect square. M must be a perfect square and also n must be a perfect square. So let's set m equals p square because it's a perfect square. So I'm going to replace p with its value. I get 2p1 quinary square, because since m is a even, which means p is a even. If p is a even, which means inside of this one must be even. Okay, which means p is a even. I'm replacing p with its value, 2p square. So this one is giving us 4p1 square. Okay, and also for n is a odd, so it's going to is also a perfect square because of the left hand side of this equation. Okay, so I'm going to set q equals 2q1 plus number 1 quinary square. Okay, so I'm going to distribute this one. It's going to give us 4q1 square plus 4q1 plus number 1. Okay, then I'm going to make this product. So we get k square, which equals m is multiplied by n. I'm going to replace mn with its value. I get 4p1 square factor 4k1 square plus 4k1 plus number 1. Okay, let's take number 4 out of these things as a common factor. So we get 4 is multiplied by this box. Okay, we don't care about this box what it is. So we get this bunch of these numbers. This one, when you multiply all these things by this one, is going to give us some expression here. So we don't care about that expression, we care about number 4. We know the whole thing is a multiple of 4. This one exactly is a congruent to 0 mod 4, which is verifying our first setup. Okay, so we get equality, we get k square is a congruent to 0 mod 4. We get this product mn is a congruent to 0 mod 4, which means this setup where we have set is true. We set m was a perfect square and n was a perfect square, then is giving us this true statement, which means m and n are the perfect square on evenness when we have k is an even. Now let's move on to the second case when we have k is an odd. Okay, k is an odd, we already mentioned k square is a congruent to 1 mod 4 by chart. Okay, so I'm going to do almost the same thing. Since you get k square is a perfect square, which means the right hand side of this equation must be a perfect square as well, as discussed previously, which means since k is odd, which means each of these must be odd. So let's set m equals p square, because it's a perfect square. We are going to assume it's a perfect square. At the end we found this one is true. Okay, so if m equals p square, which equals 2p1 plus number 1 quadratic square, because we are writing this one on the form of the odd expression. Okay, so I'm going to distribute this one, is giving us 4p1 square, 4p1 plus number 1. So let's work on the other side. We get m, we get n is also a perfect square, because the left hand side of this equation is a perfect square. So I'm going to do the same thing, 2k1 plus number 1 quadratic square, which equals 4k1 square plus 4k1 plus number 1. Okay, without doing any calculation to make this product m is multiplied by n, I'm going to reduce this one to mod 4 as well as this one. You will get to the result quickly. Okay, so this one is clearly is a congruent to 1 mod 4, because this one is 0, this one is 0, because this one is divisible by number 4, this one is divisible by number 4, as well as this one. This one is 0, this one is 0, this one is a congruent to 1 mod 4. Let's multiply this product, this one by this one. So we know we already have this equality as a perfect square, which equals m is multiplied by n, which equals this one, p square is multiplied by k square as a perfect square, which equals this one 1 factor 1. We are going to make the congruent sign, not equal sign, which is a congruent to 1 mod 4. This one is also true. We get the product, which is we get this product, which is m and n, is a congruent to mod 4. Also, we get k square is already have it. K square is a congruent to 1 mod 4 by the chart. So which means this statement is true. So which means this setup that I have set, this one, also is true, because I set this one is a perfect square, this one is a perfect square. Then as we go in the proof, we have proven this one, which means both of them are a perfect square. Okay, remember here always you're keeping GCD of m and n equals 1. Okay, thank you for watching. I will see you next video. Bye.